Hey, welcome to the bioinformatics chat. This is the second episode in our AlphaFold series. If you haven't heard the first episode, you might want to check that out for some additional context. And in this episode, I talked to Janani Durairaj about her work with proteins and shapers. But before we get to the bioinformatics, I just wanted to tell you briefly about some of the things that happened in Ukraine since we last spoke. Now, I'm going to play some sounds that are disturbing. They're not like super explicit, but if you're not sure you're ready to hear them, you can skip. I'll put a timestamp in the show notes where bioinformatics begins. And the sounds I wanted to play to you are from an Instagram video by a woman, a singer, who was sitting in a pizza restaurant in a city center on 27th of June, about 6 days after the previous bioinformatics chat episode was released. The city is Kramatorsk, which is in the eastern Ukraine, about 25 kilometers from the front lines. But the city is peaceful enough that quite a few people gathered in this pizza restaurant and they're enjoying themselves, including this woman who is petting someone else's husky dog.
What a baby I've met today.
And then, a couple of moments later, the restaurant gets hit by a Russian missile.
Аптечка є? Вам чи треба? We got shelled.
That Russian missile killed 10 people, including 2 twin sisters, who were just 14 years old, and another girl who was 17. An 8-month-old baby was wounded. Please join me for a moment of silence to remember and think about the people, the innocent people whose lives Russia has ended. Slava Ukraini. And now, on to my conversation with Janani. Today, my guest is Janani Durairaj. Janani is a postdoc at the University of Basel. Janani, welcome to the podcast.
Hey, thank you. Thank you for having me here.
Can you tell us about your scientific background?
Yeah, sure. So I did a bachelor's in computer science in India, along with a dual degree master's in biology. And then I moved to the Netherlands at Wageningen University for my PhD. I did my PhD about structural machine learning for a particular class of plant enzymes. And then now I'm at the University of Basel as a postdoc in, again, using structural approaches for drug discovery and virtual screening.
That's pretty cool. And do you remember how you first heard about AlphaFold? What did you think about it?
So I think I heard about the first AlphaFold some years ago, and there already it was making some waves, but it felt like it would be a while before it took over. But yeah, that of course was not the case. So with the new AlphaFold, it really felt like, okay, wow, this is a game changer, and I'm really happy that I picked this field.
Okay, and how is this problem of protein folding, which is what AlphaFold does. How's that related to your scientific interests?
So in my PhD, we were looking at this specific class of plant enzymes which had a lot of sequence diversity, but they shared the same fold. So it was like structure-based techniques would work so much better on them than sequence-based techniques, and that's how I got into it. And at that point, I was using homology modeling and, of course, looking at the PDV structures and so on. And I realized that there weren't as many, let's say, tools or algorithms specifically for dealing with protein structures as there were for sequences, especially in some niche applications. So then in the middle of my PhD, I sort of moved to more general algorithms that work on protein structures as a whole. It's like a really nice place with a lot of opportunities, I think, because it's not just that you go from a one-dimensional sequence to a three-dimensional structure. You also gain so much more information. Like you have electrostatics, you have the surface representations, you have dynamics and interactions, and just so much more than just the coordinates.
Is that AlphaFold that provides that information?
Now it is, yeah. I mean, before it was the PDV and probably homology modeling, and now I think AlphaFold just completely increased the amount of data that you have by just a lot, yeah.
And so you mentioned that you developed some algorithms to deal with like protein structures as part of your PhD. Can you tell us more about that?
Yeah, sure. So the problem that we were facing is that when you have a lot of protein sequences, then you can use k-mer approaches to compare them, especially if they're diverse, because at that point alignment may not make so much sense because they don't really align. So then you would use alignment-free approaches to compare these protein sequences. And there wasn't really something like this for structures, as far as I could tell. And the reason, of course, is you can fragment a structure just as you would a protein sequence. Like you could make it into k-mers, or you could take maybe overlapping spheres and so on. But then how would you compare these fragments? Because they're rotated and translated all through 3D space. And so for this, we kind of got inspiration from the field of computer vision, where they have the same problem where they want to compare, for instance, output from sensors or robotics, where you need to compare different poses or gestures. And the solution is something called rotation invariant moments. And these are just geometric formula, let's say. So it's a mathematical formula. You give as input a set of three-dimensional coordinates. It spits out a number. If you rotate these coordinates and feed it through the same formula, then you still get the same number. And essentially all that we did was we took 4 of these moment formulas, and essentially that means you get 4 numbers representing your fragment, and that's your k-mer, or shape-mer, as what we call it. So you can now divide your protein into these shape-mers, and then you just get a count matrix of all the shape-mers, just as you would with a k-mer count matrix. And you can do all kinds of k-mer-based approaches.
Is it the case that you can generate however many you want of these moments? You just chose 4, but like in principle, you could have 10 of them.
Yeah, I think there are 16 or even more than that. So they have different orders, and like finding these formulas is a whole like mathematical field.
Oh, interesting. So it's not like a parametric thing that you can generate on a whim, but you actually have to research each one separately.
Yeah. So it's essentially I can give you like an example. So one of the simplest moments, I think, is if you look in 2-dimensional instead of 3-dimensional, just to make it simpler, is x squared plus y squared. And the reason that works is if you rotate a point or a set of points, then the new x and y is some combination of cos of theta and sine of theta. And then if you do x squared plus y squared on those new set of points, because of trigonometric identities, things cancel out, things add up, and you end up with the same number. So just to find these really complicated formulas that somehow have this property based on trigonometry, that takes some time. So
you still, when you compare your proteins, you still like slice them into smaller like subunits or something?
Yeah. So you could either slice them in a k-mer way, just, consecutive residues, or you could slice them with a radius kind of way where you look at overlapping spheres of coordinates. So that way you get interactions and like spatial residues into account. Yeah.
And so when AlphaFold came out, was it like a natural connection? Did you see like a low-hanging opportunity there?
Yeah, pretty much, because so when I wrote the paper for this approach, it was like the conclusion was basically the future holds this opportunity of having hundreds of thousands of structures, so you need these kind of fast approaches to compare them. And then suddenly AlphaFold came out and there were millions, so it was like the perfect, we were really excited. And as soon as it came out, I think we tried to download it and run the whole thing. And that's when we got in touch with Pedro and we just all came together.
Can you tell us more about that? How did that contact happen?
Yeah, it wasn't actually planned. So as I said, we were really excited that this whole database came out and we immediately downloaded and tried it out. And then we were showing a friend of ours, Miguel, who's in Pedro's, he's a postdoc in Pedro's lab, but we did our PhDs together, essentially. And we were just showing off to him, like, look, it was like, it took longer to download the data set than to run the analysis and so on. And he showed it to Pedro, and then Pedro got in touch, and that's how it all came together.
Oh, very cool. Did you have to maybe somehow optimize the algorithm, given that you had to deal with this much more data?
Actually, no. So the algorithm itself, like, it was fast enough to handle this in a couple of hours. So it takes, I think, milliseconds per protein, and we could parallelize it. So the numbers were not the problem. But the actual problem was that AlphaFold models, so they come with this confidence scores. So each residue gets a confidence score. And the parts of the protein of the model which have low confidence are essentially just completely disordered. They're like flapping around these loops. And so when you compare AlphaFold models as a whole to PDB structures, you have this huge difference in distributions just because of the presence of these disordered regions. So that was kind of our first challenge, is we had to figure out how to cut those out. Mm-hmm. And for us, actually, it was pretty easy because, as I said, it's a K-mer kind of approach, or like a fragmentation kind of approach. So you could just get rid of the fragments which have low confidence. But I think this is, in general, a problem that a lot of people are facing working with AlphaFold structures, is what do we do with these regions?
So when you run your algorithm and you get these four-dimensional, scores or hashes, so then do you try to cluster proteins by similarity or something?
Yeah, so for this, what we did was actually topic modeling. I started with this whole sequence K-mer explanation, but now I'm going to give an alternative explanation from natural language processing. But
great.
So topic modeling is usually used when you have like a lot of articles from maybe a newspaper or something like that, and you want to cluster them into different topics. And the way that it does this is usually you have this count matrix of words. So you count the number of different kinds of words in each article. And then you use these algorithms, topic modeling algorithms, to try and see which combinations of words appear with each other more often. And that would represent the topic. So we tried to do the same thing with our shapemers. We wanted to see which kinds of combinations of shapemers appear more often as a cluster. And so that's what we did. And we ended up with these 250 topics, which it was really hard to name, actually, because you can't use the word fold. You can't really use the word motif because they all have their own explanations. So I think we ended up calling it characteristic substructures or something like that. And so that's sort of like a topic of a protein.
So you described these topics from natural language processing where you deal with words, right? With discrete units, and here you have this real number. So how do you bridge that gap?
Oh yeah, no, we discretize each of these moments into sort of integers so that you can, and that's actually one of maybe both the strengths and something that you have to play around with the approach, is that you can either discretize them really finely. If you're looking, for instance, at proteins from a single family, then maybe you want to zoom in on really small differences. But then in this case, when you're looking all across the protein universe, you can discretize more coarsely. And that's what we did, yeah.
And so you arrived at these characteristic topics?
Substructures, yeah.
Yeah,
Characteristic
substructures.
topics, yeah.
And so did you manage to come up or like infer their function or something? Like what do they actually do?
Yeah, so what we actually did was what we really wanted to see is if AlphaFold comes up with something new or rare, like how does it expand our knowledge of structural space? So what we did was we compared topics across the PDB and the AlphaFold database. So we looked for topics where it's like more than 90% of the proteins within the topic were actually from the AlphaFold database and not the PDB. And so that way we found like these really rare sort of a lot of transmembrane stuff. We found some really specific plant enzymes, which are apparently really hard to crystallize. So things like this, which PDB just doesn't have a lot of. And I think we found one which might even be like novel. It was like a beta solenoid repeat that has never really been seen before in this conformation. And that's kind of what we wanted to do, show where it sort of improves or where it goes beyond what's in the PDB.
Mm-hmm. And so the reason you discovered these new topics, was that because those proteins just were absent from PDB?
Yeah, it could be multiple reasons. Like, for instance, for transmembrane proteins, it's just known that they're not very easy to experimentally characterize. So there are a couple of them, of course, in the PDB, but AlphaFold essentially completely expands that space. Like, it makes way more transmembrane models, and now people working on transmembrane proteins just have so much more information to use.
Oh, very cool.
Yeah, and then in some cases, of course, with the really novel things, like the things that you just don't see in the PDB at all, it's hard to tell what to do with that, because you could say maybe you got it wrong. Like, how do you prove that really exists? So, yeah.
Yeah. So you have discovered these potentially new structures, right? What are your future plans regarding them?
First of all, of course, we're going to repeat the whole thing with the new AlphaFold database, which I think has more than 1 million structures. And the first idea is to do like an evolutionary analysis where we try and see which kinds of species have these characteristic substructures in common, or maybe it's something related to ligand binding or metal ion binding, or interfaces and so on.
So you said that's first and...
Oh, yeah. So the second thing, of course, is to really pinpoint these novel structures. So this is something that we weren't really sure how to do in this first analysis, because you can compare it to the PDB. But yeah, there are some challenges to face. For instance, this topic modeling approach, it kind of weights repeats really high. So if you have the same word repeating over and over in the document, of course, then you would assign it with more weight to a certain topic. So we want to really see if the improvement is that AlphaFold is really good at characterizing these really long repeated elements, which are already present in the PDB as 1 or maybe 2 repeats, but now we have 10 or 15, or if it's actually something that we've never seen before.
And how does your algorithm deal with these repeated elements? Does it like record their number or something?
Yeah, so in the end, the input is this count matrix of shapemer. So there you can tell if it's being repeated or not. Exactly. Yeah.
I see.
Yeah, and the third thing is, of course, to compare it to what's known already. So, for instance, if it's a ligand binding kind of fold, or if it's something related to protein-protein interface, or if it's just for stability and these kinds of things.
And what was your experience like participating in this, group or community effort? Were there any interesting, interactions between different groups that you're part of?
Yeah, it was really nice, actually. I mean, it was also like a huge effort, and a lot of these people, I'd only read their papers, so I was very excited to be on a Zoom call with them. And everyone was involved in each other's work, in the sense of they'd read it and they had comments and recommendations and so on. But at the same time, everyone was doing their own thing. So it wasn't maybe as stressful, let's say, as a bigger collaboration where you really have to coordinate everything together. Yeah.
Cool. Anything else you wanted to talk about?
Yeah, there was one other thing I actually wanted to mention. So maybe I think 2 months ago, around the time that AlphaFold came out, we at the University of Basel, the Tertiary Street Group, we started this structural bioinformatics newsletter because we realized that the number of papers that use structure now is just starting to explode. Like every time I open Twitter, there's 2 more, and I didn't want to miss any. So yeah, if you're interested in structural bioinformatics, then that's a nice place to stay up to date. It's called Folded Weekly. Yeah.
Okay, awesome. Yeah, we'll put a link in the show notes. Cool, Jay. Very nice project, and we wish you best of luck in your future research.
Thank you.